Hey everyone, thanks for having me at Munich Data Geeks. Yeah, I'm going to tell you about this project that we did with my team at Yelp for ad budget allocation. And first of all, just a couple of words about me. I'm Samuele. I work as a applied scientist in the recommendation intelligence team at Yelp. But before that, I was working in the ad budget allocation team, and this project is from that time. Before that, I worked as a data scientist in multiple industries for 5 years, and then a couple of years ago, I moved to Munich to join Yelp. My background is in statistics, and I'm also a blogger. For many years, I wrote blogs for Towards Data Science. And then more recently, when Towards Data Science left Medium, right now I'm working for a different, I'm writing for a different publication on Medium. So first of all, in case you're not familiar with Yelp, Yelp is a platform that connects people with great local businesses. That's the mission. And it's quite popular in North America, so especially US and Canada. We have around 74 million people that visit our app, our website each month. And just to give you an idea, our annual net revenue is around $1.5 billion. And how does Yelp make money? This is also relevant for this talk. Like many other social media, Yelp makes money through targeted advertisements. So basically what our advertisers do is they have a budget, they set a budget, a monthly budget typically. Let's say I want to spend, I have a budget of $300 for my small business. Then we try to use that money to buy basically impressions and clicks from our users. So if you look for burgers, let's say, or electronics, you'll also get some sponsored results, and that's what advertisers pay for. So this project I'm going to tell you about is a backtesting engine for ad budget allocation, and I also wrote a post on the Yelp engineering blog. So if you are interested, you can find more details there. So let's start from from a very simple view of the campaign journey, let's say. So as I said, advertisers set a monthly budget, but the way how our system actually works is that every day we need to decide a daily budget. And then with that daily budget, once that daily budget is set, based on that budget, during the day, the ad will receive impressions that can convert to clicks, that can convert to leads. And then at the end of the day, once we have recorded, the number of impressions, of clicks and leads, based on this number, we can charge the advertiser. So based on impressions, clicks, and leads, we can compute the daily billing for that campaign. And so the system that my team was working on was a system that basically handles the daily budget, so how to set the daily budget and where to allocate the budget, and the billing at the end of the day. So let's say that we manage these two parts of the process. So what makes things complicated is the fact that there is like a feedback loop, right? Because the decisions that you take on day one will affect what will happen on day two, and so on for the rest of the month. And this is like one of the most important points of the talk, because this feedback loop is the whole reason why we had to develop like, let's say, a more sophisticated simulation engine, rather than just relying on estimates, on simple methods to estimate things. So now this is the process normally when you, as I said, we handle the daily budget and the daily billing. So that means that we have algorithms, we have code that handle this part of the pipeline. And what happens typically is that, of course, you want to try new things to make your budget allocation process better, to make your billing process better. So what you would do typically is, first of all, you design an algorithm, and then you implement the code. And then when you think the code is good enough, you are ready to test that in the real world, typically with an A/B test. So let's say you split your campaigns randomly and you send half of your campaigns to the existing algorithm and half of your campaigns to the new algorithm. And then if the performance is good enough, is the one that is better than status quo, let's say, then you promote this new algorithm. This is perfect. Like, this is the golden standard. But we have a couple of problems in our case. First of all, we are talking about like our campaigns are in the order of hundreds of thousands. So there's not like millions where you can leverage A/B test because of the statistical properties. So the data is relatively small, and most of all, we need to wait a lot of time because the budget is monthly. So when you make a change, you want to observe how the new algorithm will perform over at least over 1 month. So because of this, A/B testing is really, let's say, expensive in our case, because when we reach A/B testing, we want to be reasonably confident that the new algorithm is actually good enough, because we can't test a lot of things because of the two reasons I mentioned before. So that's why that's where the need for back testing comes from. So back testing is basically a new layer where, after we have implemented the code, we can back test the new algorithm, the new change we want to try. And so we can, of course, this is like it's very scalable because you can backtest pretty much anything, and it's not expensive at all. And you can backtest like hundreds of alternatives, of options, and then at that point you can be confident enough that the thing you are going to test is actually good. So this is, I just want to clarify just a small nomenclature thing. I will be talking about backtesting because it's technically we test this algorithm on the past. Other people will call this simulation. So I think in this case, this is something in between backtesting and simulation. I prefer the naming backtesting because I always want to make clear also with the internal stakeholders that this is just, you know, the performance that we would have had in the past. So don't expect this thing to happen next month. That would be more properly simulation. So I'll call this backtesting, but let's say simulation and backtesting are almost synonym in this case. So this is the architecture of what I call this backtesting engine, and yeah. So the rest of the talk will just be I'll go through each of these components and explain what they are and what they do. So the first component is basically just a very simple YAML file. It's a dictionary where we define the variables that will enter the simulation. So typically we have a date interval. Let's say this could be like last month. So in this case, from December 1st, 2025 to December 31st, 2025. And then we have an experiment name, of course, that's just for tracking. And then the relevant part is this one. It's where we define the search space for the parameters that we want to backtest. So in this case, we will use scikit-opt, which means that there is an optimization that tries to find, you know, the best values for our parameters. And because there is an optimization, we need a metric to optimize. In this case, it's average cost per lead. So because of course we want to like the best experience from the point of view of the advertiser is if they spend as little as possible for a lead. So from the point of view of the advertiser, we want to minimize this average cost per lead. And then we have a maximum number of runs, or maximum number of trials for the simulator to try. And then depending on what we want to test, we have as many parameters as we want. In this case, let's say that we have, this is of course just a fictional example, we have the name of the allocation algorithm, which may in this case status quo, or the new algorithm that we want to try, algorithm X. And let's say that algorithm X also takes as input a parameter called alpha, and alpha is a real number between -10 and 10. Yeah, we are using this scikit-opt object to define our search space. So after we have defined our search space, then it's the time for scikit-opt. So what scikit-opt does at the first iteration is it just picks some values at random from our parameter space. So in this case, let's say that the parameters that are extracted at random are status quo for the algorithm and 3.53 for alpha. By the way, in this case, because we are using status quo, alpha is not even used. But of course, scikit-opt doesn't know about it. So now the most important part. We have the production repositories. This is where like I would say was the most important part, because this project, because before it had this architecture, was in a Jupyter notebook. So as you can imagine, you have a lot of like business logic in your repositories, and if you try to do this in a notebook, you have to basically copy all that logic in a notebook, and it's like a nightmare, first of all. And second of all, you can never be sure that you are doing exactly what is in production in that moment, right? So you can be reasonably confident, but it's like a nightmare, because you have to constantly update it, and the notebook becomes like unmanageable. So when we decided we wanted to invest more on this backtesting engine, we had to find a different way to do things, and I think the best tool for us was using these Git submodules, because Git submodules allow you to basically use some Git repositories inside your repositories, but you don't have to copy anything, because they are just linked to those repositories. So by doing that, that means that basically we could like when we want to simulate a new algorithm, all we have to do is we go on the production repository, we open a new branch, we develop the change that we want to test, and we can directly simulate it inside the backtesting engine. And that's quite amazing, because once the result of the simulation are good enough, and you want to promote that thing into production, you don't have to do anything, basically, right? You just push that branch that you have simulated. So that allows you to be completely sure that what you are simulating is actually what goes into production. And as I said, like if you try to do this in a different way, like whether it's a notebook or whether it's like a different repo where you try to copy the logic of the production repo, you can never be 100% sure, and there are bugs, and there are, it's very hard to manage. So in this case, Git submodules are really the ideal application for this kind of project. So basically we have the candidate parameters, and that we feed to the production repositories, and the output is before that, of course, we also need to, because it's a back testing engine, as I said, we need to use historical data, because as I said, we have a time period, so typically last month, and there are things. So basically we take the campaigns that we had last month, and those campaigns have some things that will not be affected by our simulation, right? Some variables, some characteristics. The simplest example is like the campaign age. If the campaign has been on for 2 years, for 3 years, for 3 months, that doesn't depend on the simulation. So we read all these data that are not affected by the simulation from Redshift in this case. But of course, we have to simulate things. So the problem is that if we take historical data and we see that on that day, that campaign had a budget of $10, we know how many impressions and how many clicks that campaign got on that day. But of course, because we are testing a different algorithm, it may be that that campaign on that day in our simulation will have a budget of $13. So we don't really know how many impression, clicks, and leads the campaign would have had if we had this new algorithm in place. And that's the whole point of having machine learning. So basically, we need this component for the what if, right? Because this new branch from our production repo, we will change the daily budget. We change the daily budget. So we need machine learning models to know, to have a reliable prediction of what the impressions, clicks, and leads would have been if we had a different daily budget. And these models are of course trained on this data. Yeah, we also monitor, of course, these models to make sure that they are, good enough. You always have to keep in mind, like, what's your baseline, and before we had this thing in place, the baseline, if we wanted to ask, like, what would happen if we use this different algorithm. Before that, basically the baseline was some napkin math. So, I mean, that's not super hard to beat as a baseline, to be honest. But I would say that in general, this approach, this engine, was, I mean, we tested it over time, and after we simulated things and we rolled out the new things that we were testing, with an A/B test, we could, of course, measure, like, what the difference was between our simulation and what we actually observed. And in general, we saw that it was quite reliable. And so I think that, testing it on real data, in real life, gained some trust from the other stakeholders, because they were seeing that the results that we are getting were actually reliable. Okay, so now that you have all these inputs, like the candidate input, the candidate parameters, the production repository, the data, and the models to predict what if, you basically throw everything to your production repo, and you get like the result of the simulation, which is basically what would have happened last month if we had used this new algorithm. And we have many metrics, but let's say some of them are average cost per click, average cost per lead, and our margin. So basically the difference between the revenue that we get from the advertiser and our cost. And and so in this case, as I said, we want to minimize average cost per lead, but typically the actual target is a bit more complicated than that. And then we have other metrics that we track. And then the process is quite intuitive. So basically, after the first run, we have a candidate, we have the resulting metrics, and then we pass them to the optimizer. And the optimizer proposes a new candidate, and so we get new metrics, and the process goes on like that. In this case, it goes on 25 times, because we set number of runs equal to 25. So we get 25 candidates and 25 sets of metrics. And hopefully, because of the optimizer that is trying to, it's agnostic, so it doesn't know what happens here, because it would be very complicated. But just given the input, it tries to minimize our metric. And so hopefully, like, each candidate is at least on expectation. It's expected to be better than the previous one. And then I guess we have something in common. So we log all these candidates and metrics on MLflow, which makes it easier to share the results also with other stakeholders, because it has an intuitive visualization, and so from there we can see like what candidates are more promising, and we can decide what to actually try with A/B testing in production. Thank you.